Okay, so we're still talking about cross product, and there are some nice applications of the cross product. So we can use it to find areas and volumes, believe it or not. So here we're going to use vectors to calculate the area of a triangle whose vertices are this, and this. So A, B, and C. So I guess A, B, and C are located here. We want to find the area of this triangle. So that might be hard to do, but we're going to do it fairly easily. So they say the trick is to recognize that any triangle can be thought of as half a parallelogram. So here's the triangle, but here's the parallelogram. And that the area of a parallelogram is obtained from the cross product. Well, that sounds a little bit strange because the cross product is supposed to give us a vector. So how does it have anything to do with this area? It's supposed to give us a vector. So they're talking about AB and AC. So these two vectors, how does that have anything to do with the area? It's a vector. It's a vector perpendicular to this plane. But what is the length of that vector? So if we go back and check the length of A cross B, A cross B, the length is what? The magnitude of A times the magnitude of B times the sine of theta. So maybe this gives us the area because they're saying that the area of the parallelogram is this. So maybe this gives us the area of the parallelogram. Maybe. So she is asserting here that the area of this triangle is half of the norm of the cross product, which we haven't shown that yet, but that's what she's suggesting, and that's what we would have concluded based on the definition that that's the direction she's going, but we haven't proved it yet. So the area of this is the area of this parallelogram is the norm of this, because like we said before, the norm of this is the norm of A times the norm of B times the sine of the angle between them. So apparently, and I can't say I remember this, that the area of a rectangle can be obtained by the length of this times the length of this times the sine of the angle between them. I definitely can't remember any formula like that, but I guess you can look it up. But just one thing I'm going to check, and that is, what if the angle is really small, like close to 0? Or even, let's say, what if the angle is 0? Then what? Then we have no area, and the sine of 0 is 0. So at least for that doesn't show anything really, but at least it doesn't contradict anything either. Okay, so if we take that fact as true now, then going back to this, we have these 3 points. So we can write so in order to find the area, we need to find A and B. So we have A, B, so we need to find the vector that connects them. And we need to find AC. So they do that here. AB is, so now they say, what do they say? To compute the cross product, we have to think of A, B as vectors in R3, because to do cross product, our vectors have to be in R3. So AB, they say just imagine that the K component is 0. So AB is written as minus, AB is, I guess, minus I minus 2J, but we can add in the minus 0K as well. And then AC, we can also have, imagine it in three dimensions, in R3. So now we can do AB cross AC using this determinant method, and I guess we end up with this, so that the area is equal to the norm of this 1/2, which is 7/2. So I guess that's quicker. But to be honest, I don't remember this, that the area of a rectangle comes from this length times the sine of the angle between them. So I guess we have to look that up somewhere. Okay, let's let's try this one. Find a formula for the volume of this thing. They call it a parallel pipette, determined by the vectors A, B, and C. So we have the vectors A, B, and C, then we get a parallel pipette if we extend everything like this. So I guess in section 1.3 they said that the volume of a parallel pipette is equal to the product of the area of the base and the height. So take the area, this area, times the height, which is this thing here, this length here. That's going to give you the area of a parallel pipette, supposedly. Again, I don't remember that either, but apparently they explained this one in section 1.3. In figure 1.58, here, the base is the parallelogram determined by A and B. We just sort of showed that. We just showed that. So, and we just worked with that. So A cross B, the norm of that is the area. Hence, its area is the norm of A cross B. The vector A cross B is perpendicular to this parallelogram, right? So here's A cross B is perpendicular. The height of the parallel pipette is C cosine theta, where theta is the angle between A cross B, which is here, and this C. So I guess if this is C and this is A cross B, then I guess we're talking about the projection of C onto here, and we just want its length. And I think we worked that out before, where you can just probably see it from simple trigonometry. But either way, this length is going to be the norm of C, the length of C, times the angle between this and this. I'm sorry, times the cosine of the angle between this and this. Okay, so you can either use the projection to get that, or maybe some trigonometry to get that. So now we know the height of the parallel pipette. We know this area. So the area of the parallel pipette, the volume of the parallel pipette, is going to be the area of the base times the height. The area of the base is A cross B, and the height, this thing, is this. And this can be written like this. Why is that? Because if we take the dot product of this times that, then what? That's equal to, remember the property of dot products that include the concept of cosine, is if you take the dot product of one thing times another, then it's going to be the length of this thing, or the norm of this thing, times the norm of this thing, times the cosine of the angle between them. But the cosine of the angle between them is theta. So it's the length of this thing here, the length of this thing here, and the cosine of the angle is cosine of theta. And then why do we have the absolute value? Because here we have absolute value, so here we can put absolute value as well. And they even say that since we have this cosine in here, that means that somehow that can alert you that maybe you should try and express this as a dot product. So for an example, suppose we have A, B, and C. So an A, a B, and a C. And then we can say what's the area of the parallel pipehead determined by it, and it's this. So if we have this A, this B, and this C, then we do this to that, and we get this. So the area is 132, which I guess is a lot easier than trying to figure it out some other way. Okay, so the next thing she says is that the real number A cross B dot C, so this is a vector dot another vector, that's a number. And that appears in example 5 here, is known as the triple scalar product of the vectors A, B, and C. Since this represents the volume of parallel pipehead, it immediately follows that this equals this. So I guess because this is a parallel pipehead, but then this is also going to represent the same, I guess going to be the same parallel pipehead, and this is going to be the same parallel pipehead. So their areas all have to be the same so that you can get this identity, that this equals that. Because they all are, we have the same components for a parallel pipehead, so we're talking about the same parallel pipehead. So instead of having to prove this thing, they said this is a nice example of how the geometric significance of a quantity, of this quantity, can provide an extremely brief proof of an algebraic property the quantity must satisfy. So try proving it out by writing out the expressions in terms of components to appreciate the value of the geometric insight. So we saw this because of geometry, but if you had to really prove this using algebra, it would be a lot of work. And then she says, we leave it to you to check the following beautiful and convenient formula for calculating the triple product here. So that this turns out that you can, to get this, you just put A on the top row, B on the next row, C on the next row, and you'll get the triple product. But they don't explain where that comes from. Okay, now torque. This is when you turn a bolt. I guess when you turn it, pull it down this way or pull it down this way. Which direction does the bolt move in? It turns out that it moves, turning a bolt with a wrench, the torque on the bolt is the vector R. Here's R. And then you put some force on it. You apply some force like this or straight down. So that's going to be, this is a cross product. So that means this is going to be perpendicular to R and F. So it's either going to be in this direction or that direction. So I guess it's, if you're rotating this way and you use your right hand, it's hard for me to use my right hand, but it's going this way. It's going into the wall or something like that. Okay, so anyway, but the other thing to notice is that the torque, if it's the cross product, remember the cross product has the sign in it. So what does that mean? If the angle between R and F is perpendicular, so if R is here, then F is perpendicular, not like this F, but straight down instead, then you get the maximum torque, which makes sense. If you're applying an F like this, you're sort of wasting your energy. You want to apply it directly down, so you get more response or more torque. But we're not going to go into this. We're not going to go into the physics problem here, but you could read it here. Or this is another example. the motion of a rigid body, but we're not going to go into that either. So reviewing, dot product is scalar. The formula has a cosine in it. The magnitude is maximized when they're parallel to each other. If they're perpendicular, then it's 0, right? Or, of course, if A or B are 0, then it's also 0. A dot B does equal B dot A. Associativity is irrelevant because this doesn't make sense. Why does this not make sense? Because this is A dot B is a scalar, so you can't do a scalar dot C. You have to do a vector dot C. So this doesn't make sense. This makes sense, and this is true. And if A equals B, then A dot A. I think that's a mistake. That's a mistake. If A. Okay, I don't know what this means actually. Okay, for the cross product, the result is a vector. It's a vector perpendicular to A and B. Its magnitude has the sign in it. It's maximized when they're perpendicular. It's 0 if they're parallel, because the sign of 0 is 0. It has this property called anti-commutativity. It's not associative, so you can't do A cross B cross C equals A cross B cross C. You can't do this. It has this kind of distributivity, and if they're perpendicular, then the norms are the norm of the cross product is equal to the products of the norms. So remember, this is a cross product, but this is just scalar multiplication because it's a number and a number. But this works only when they are perpendicular. Okay, next we want to do section 1.5 equations for planes and distance problems. So we're going to come up with some kind of equations for a plane. So, and of course we need to identify what plane. So we're talking about a plane that has some point P sub 0 in it, but that doesn't tell us which plane it is because there are infinitely many planes that have P sub 0 in it. But the plane that has P sub 0 in it and that is normal to n. So if I just told you the plane which is normal to n, there's an infinite number of planes that are normal to n. But we're talking about the plane which is normal to n has P0. There's only one plane like that. So, and they denote it by pi, capital Pi. So, what's the equation of this plane? Well, this is one way to write it, and this is a vector equation of it, because this is a vector and this is also a vector. And then we can go from here, we can get this. So this is another way to write the equation of a plane. Let's just look at this for a second. So, first of all, what are A, B, and C? A, B, and C are the coefficients of n. So n is equal to AI plus BJ plus CK. So that's where the A, B, and C come from. And what's x0, y0, and z0? That's the coordinates of this point P0. So we get this. If we work it out, we're going to get this. So, the thing is that this is an equation with 3 variables. So where are the variables? So this is not a variable. This is x0. That's the coordinate of the x coordinate of p, and so on. y0 is not. z0 is not a variable. So the variables are x, y, and z. So this is an equation in 3 variables. And this equation in 3 variables will represent or correspond to this plane. What does that mean, that this corresponds to this? It means that if you take any point in the plane and put its coordinates take the coordinates of that point and put it into this equation for x, y, and z, this is going to be true. And furthermore, anything that solves this equation, any combination of x, y, and z, if you think of that x, y, and z as a point, it will be in this plane. So there's a one-to-one correspondence between the points in the plane and the solutions to this equation. But we can rewrite this like this, where you're going to get ax minus, you're going to get minus ax0, you're going to minus by0, right, when you multiply this times this, and here you're going to get that. So these are constants, right? A times x0 is a constant, b times y0 is a constant. So you can combine those all into one big constant, call it d. So here's d. So then once you do that, you're going to get this equals d, or you can work that out. You're going to get that equals d. And so this is another version of the equation of a plane. So whenever you see an equation like this, this will be the equation of a plane. Now there are many other shapes that we can think about in 3D, in R3. We can have all kinds of shapes, all kinds of surfaces. The plane is a very particular type of surface, right? We could have like curved surfaces or whatever. You could have like a mountain or a valley, right? Or all kinds of other shapes. But whenever you see an equation like this, the solution set for this equation is going to be the set of points that form a plane.